Not tonight. Like tonight and tomorrow. To start studying.
Okay, hello everybody. How's it going? Hanging in there? Administratively, any questions about what's happening? On February 28th, we have our first project-related assignment due. So please start working with your groups. It should not take that long to fill out the forms and everything. There's a part where it asks for like about 150 words of a description of what you're thinking about doing. That can change. It would be nice though if it was in a general area, because I do plan to provide some feedback for your team so that you can hopefully move forward more efficiently. Okay, so please keep that in mind. And we seem to be in a general rhythm, I think, on the labs and on the post-lab assignments. That rhythm may change a little bit as we get a little bit further down the road, but hopefully you'll find that the post-labs reinforce with the lab speech. And I kind of feel like this part of the class is the medicine, right? So, or your exercise workout before you get to perform and do things. So thank you. So hopefully we can have a discussion, right? As you're realizing, we covered more of the theory. In particular today, will be very heavy on the math and I guess the background information without so much in terms of the application. But hopefully we'll be able to talk about things and things like this. But any comments, any thoughts? How's the class going? Yeah, okay. I think the Leonard Jones potential problem was significantly harder than some of the other ones, right? I think you probably agree with that. Please feel free to contact me during office hours, which are before Tuesday's class and after today's class. And then we have the TAs with our office hours on Mondays and Fridays. Okay. All right, well, and I think now most people, if they want to get in touch with me, they're using Canvas Inbox. So thank you for doing that. That helps me make sure I get to you within a timely manner. Okay. If it goes to the inbox, the email inbox, you'll be with a bunch of other stuff. Okay. But the Canvas Inbox, I try to make sure I clean, I'm checking that, cleaning that out. Responding appropriately, okay? Okay, so today is an opportunity to have what may be your first exposure to finite element analysis or the finite element method. And for many of us, we don't spend that much time on the math for this method. We spend more time on the applications, using different software packages, whether they be open source or whether they be commercial packages. So this may be the only time you get an in-depth look in your career at what's kind of going underneath the hood. But for others of you, this might be the beginning of a beautiful relationship that you have with numerical, or further your relationships with numerical methods. And the finite element method is definitely key to them. You may ask yourself, why do we spend so much time working on problems that don't have mechanics in them? And I think we talked about this earlier in the class, but the heat transfer problem, this induction problem we're doing, is a pretty straightforward partial differential equation, right? You have the Laplacian operator, and we have a heat flux, and so diffusion, it just works really nicely with partial differential equations and the math. Like you can see, we have some You'll see it again today. We can do some of the analytical solutions by hand, at least for 1D. As you start building up, and we will start building up the physics, you'll see that mechanics actually, even though it's more intuitive to many of us, and especially since we've taken mechanics and materials at this point in the undergraduate curriculum, and maybe we haven't taken the fluids yet, haven't taken the heat transfer, some of these concepts seem more advanced analytically, at least the way we think about them in the curriculum, but mathematically, when it comes down to their roots and what the PDEs are, they're actually a little bit simpler, at least from the perspective of simulation. Okay? So don't worry, we will get to mechanics. We will get to mechanics. Nonetheless, we are kind of building up our arsenal of dealing with partial differential equations. The last time we met, we discussed the finite difference method. And that might have been a little bit life-changing, or at least maybe gave some perspective in terms of how we take these differential equations and we use somewhat simple expressions with discretized space and time to be able to come up with simulated results. So we're going to essentially continue on a similar arc, and we'll be looking at kind of parallels to what you see in finite difference, and essentially building from finite difference to the finite element. Okay. So for today, we're in our transition from finite difference to finite element. We'll talk about the weak form of the heat equation and a little bit about what that means. We'll talk about this idea of introducing trial test or basis functions, and we can also discuss a little bit concerning the accuracy of FEM. A lot of this may seem like jargon, okay? And it kind of is. And so it will maybe make you look smart in an interview, maybe, okay? Or at least you'll be able to be like, yeah, there was that time where this dude talked to us about these different things, and in the end, I'm just like grateful that we were doing MATLAB and ANSYS. And that may be your perspective after today. Okay, so any ideas? You can look at the slide, but any ideas what finite difference method might be good for and why we might not use it? Like any applications? Where do you see yourselves wanting to use the finite difference method? And where do you see yourselves saying, maybe I need something better? Or maybe not better, that's too subjective, but I need something else. Any ideas? What do you think? Yes, go ahead.
Finite difference has been good when our turkeys are square.
Yes, it's good when the turkeys are square, yeah. Okay, yeah. Well, you could have a commercial software, right, that would implement finite difference with a more, better, I don't want to use better, it's too subjective, more complicated or intricate geometry, right, potentially. Okay. So that's a good point. When your turkeys are square, go with finite difference, which is essentially net. Okay, so yeah. Any other ideas? Yes?
Maybe like beam deflection, like just simple.
Okay. So interesting. Okay, so like again, so the math, the simulated math that we'll use is based on the finite element method usually for those types of problems, and for mechanics problems for beam. Yeah, sure. I mean, you could envision trying to, for 1D geometry, trying to implement the finite difference method. Okay. Yeah. Any other ideas? So finite difference method is applicable in these situations where you have a Laplacian operator. So that second, right, like the gradient, the gradient of the gradient essentially. So if you have mathematical problems that are posed that way, finite difference can be good. So like fusion problems, even some stuff with electric fields, you might find that you want to use finite difference. But as you'll see today, just like we went to Verlet over Euler, sometimes when people start playing tricks with algorithms, they can get accurate results with fewer iterations. And so the post-lab that you'll get to do is forcing us to make a comparison between doing finite difference in MATLAB and doing it in ANSYS. And you're like, well, of course, I want to just do it in ANSYS. That's going to be easier. We're also talking about the number of nodes you have to use. Now, yes, there might be more mathematical calculations involved with fewer number of nodes, but what you'll see is that finite element can be pretty fast. Okay, and yeah, we haven't really optimized the finite difference algorithms because we're just using for loops in MATLAB. Nonetheless, you'll see that you can get away with fewer nodes when you use finite element analysis for certain problems. Okay, that is something that you'll get to see in the post lab for this section. Okay. Have you used any of these packages? Have you used any of these packages in your experience at this point? Either in research or internships or like on a Friday or Saturday night? Okay. No? All right. Yeah.
Yeah, I think we used FreeCAD.
Yeah. So we used calculus. Okay. You might not have known it was calculus, but FreeCAD uses calculus in there, and we use pre-Max as well, and that is also based off of open source calculus. Okay. So you have, if you did basic advanced materials with me, you have done that. Okay. Elmer is an open source package. It's kind of more multiphysics-y, so you can bring in different physics. Play with it a little bit. Like calculus and Elmer, they're more. I mean, Elmer has a user interface, but they're more about the code that solves the problem. So then you find when you use some of the open source available codes, you're going to be using some of these open source GUIs. Max was the one that we used, FreeCAD, right? Another one's called Salome. The ones above, Abacus, ANSYS, and COMSOL, these are big-time commercial packages that we will use and cost lots and lots of money. Okay? But we're fortunate that ANSYS has a student license, student version that we can use. So I guess maybe now's a good time to remind everybody that we're going to be using the version 2024 release 2. Okay, so some of the videos were done in 2023 release 2. Okay, a lot of them actually, and I'm checking to make sure that the stuff works in the 2024 version. And from what I'm seeing, you should be just fine. Okay, and I'll make any notes, or you can call me on notes. I'm actually hoping that some of the bugs that were present in 2023, they've kind of worked out. In particular, and it's not relevant, it shouldn't be relevant, well, it could be relevant actually, in this week of work. We've had issues in the past with the parameterization of problems, the design points, but hopefully it'll be very stable. So that's the one. You can go ahead and you can download this for your own computer. You're just going to use the student version. Okay, if at the end I can maybe if we have time I can kind of just show you where that is. Now, the finite volume method is often used with fluid mechanics problems, and we'll cover this. We'll actually cover this method. It's a little bit different than finite element analysis, and ANSYS is interesting in that they bought over the years different companies and different softwares, and you'll kind of see that. Even as you do this first example, the user interfaces for different parts of the problem look very different. Workbench looks different than Space Claim. And they have a modeler, and you have, it's just like, you can just see where they put together different packages, and they combine them all together. So, I guess ANSYS also allows you to do the finite volume method, okay, for the fluid problems. And if you were interested in kind of going back more to the particle methods we talked about, and they have their uses, turbulent flow, for example, with X flow, and I guess the SO owns them now. You can use these lattice Boltzmann techniques. Right? So you still kind of have these kind of larger particles that are moving around, and they're not the size of the planets or anything, or the galaxies or anything like that, but they're just kind of larger than the atoms and the molecules that we've been talking about this one. Okay. All right, so someone mentioned they don't like doing square turkeys anymore, all right? So this is kind of your gateway if you want to do, these are more complicated than that. ANSYS is the way to go. I hate to break it to you though, we're still going to be looking at square turkeys though, okay, for another week, all right? And why? Well, the reason is to attempt to reinforce how we look at convergence over geometry. Okay? What are the two ways? You all tell me. What are the kind of the two ways you determine convergence when we were? What were the two ways that we could determine convergence when we were looking at time step-based simulations for particle dynamics? The two ways. Yes.
Making a graph. I guess the time step versus energy.
Okay, so making a graph versus some component. And what were you looking for with that graph?
You're trying to see when the value of the time step, so the I is positive.
Right. Right. So what we were trying to do is, right, we're looking the convergence, and this is one way to do it, was looking for when we decrease the size of the time step, and there'd be a small change or insignificant change of some percentage in whatever parameter we were interested in studying. Okay. So if we're doing turkeys, what do you think we're going to be looking at as our parameter that's of interest? It was a little bit tricky with the particle dynamics. There were actually a few different ones for the Leonard-Jones. You could have looked at energy, you could have looked at momentum. I looked at the velocity of one of the particles. What do you think we're going to be looking at as our metric for the turkey problems in terms of trying to assess convergence? Yeah, sure, Federico. Temperature, right? So we're going to be taking the temperature maybe at the middle, even the average temperature, whatever it is, we're going to be looking for that temperature to kind of stabilize, right? So that as I decrease something, time step, we're not going to play with time step too much. We're going to let the automatic solver do it. But as I decrease the space size, my discretization, I get to some type of temperature, and it's not changing. Okay, so that's one way to do it. Look at how making things smaller, time, space, elements, increasing the number of nodes, how that affects your converging on some particular value of interest. What's the other way to do it? What's the other way to determine convergence? Yes?
You get to within a certain value of what you're expecting, plus or minus 2%.
Okay, so certain value what you're expecting, yeah. Let's say you're comparing to ground truth. Okay? So you've got, for example, the geosynchronous orbit problem, all right? And we know we're going to be somewhere every 24 hours, right? So we're comparing to that ground truth. That's the other way. So those are the two ways you want to demonstrate convergence. And if you look now under the group projects module, you're going to see that you need to have one of your checkpoints, one of your assignments is going to be demonstrating that you do get convergence with the simulations that you're choosing to run. And so you're going to need to probably, in finite element world, the most common way to do that is to keep decreasing the size of the mesh, making the mesh smaller and smaller and smaller. That adds more nodes, adds more elements, and costs more computation, right? And that makes sense, right? That you're going to want to keep adding until you get enough representation to simulate what you're adding correctly. Okay? The disadvantages of finite element are that it can be a little bit tricky mathematically, and you'll see that today. And it can take up some some space. So there are people in the department and also academics and general engineers and scientists who will take either through machine learning techniques or other methods. They've been doing this for years, not just since machine learning, but simulate behaviors and then trying to reduce the order or make the models more simplistic. And one way in which we do that is by creating lump parameters that have meaning. Okay, so what are some lump parameters that you use in your everyday life when you're describing mechanical systems? What are some of the lump parameters that we think of? Now when I say lump parameters, like these are, like I could, for example, model something, right? And then I could look at whatever displacement, temperature, forces involved, right? And I could then like get nice distributions and like, I can see, oh, this is what's happening in the structure. But what would be a lump parameter that I could use instead if I want to get a fast estimate? Yes? Yeah, so, well, that's electrical. I was thinking, it's often the circuit models are what we think of when we think of these lump parameters. So you have resistance, capacitance, inductance, okay? And then what are the analogies, or what are analogs? And there are actually two ways of looking at these analogs. What are the analogs in the mechanical world? Hold on. So inductors and capacitors are energy storage elements. Where do you store energy in mechanical systems? Yes. Springs and masses. Okay? Those can be considered energy. So depending, there are actually different circuit analogies where you have one as a capacitor and one as an inductor. But those are your two storage elements. Okay, the springs and the masses. Right? And so you have now, right? So then the lossy element would be analogous to the resistor. And so that would be in mechanical world and dynamic systems. If not mass, if not spring, then the damper, right? Okay. So those are your three. So those are often these parameters that we're interested in studying. So when we did our finite element, when we did finite element and when we did our whole thing on mechanics, right? We were looking at, delta equals PL over EA in mechanics and materials. Remember that? Okay? And then we said, actually, if I just want to say delta equals K delta, or if I want to say force equals K delta, right? Then I can say, that K is equal to EA over L. Right? So you can run a whole finite element simulation. And then you say, I can estimate, if I'm interested in the response between this point and this point, I can describe a K, a spring constant, that's going to give me the relationship when I apply a force here. This is how much I expect to displace relative to this location. Okay? So this is a way you can build up your finite element model, and then you can try to use the first principles or principles we've been teaching to kind of simplify and expand and be able to apply to other situations. Okay, so this is the 1D heat equation that we discussed last time. Alright, and we've kind of already discussed how we can create the center difference, the forward difference, and the backward difference versions to describe the first and second derivatives. And so this would be the second derivative, and this is the center based approach. So we have now taken this finite difference expression and we put it in the heat equation. Okay, so this over here is, well, I mean, this over here, right? This is a spatial derivative, and then this one over here is a time-based derivative. And if we break this up and looking at the space, and we look at it in terms of the time, right? We have kind of two things that we're discretizing. And we can write out something that looks like this. So the change in temperature is delta T. Right, we can think of as being now an alpha, and we take the delta T, the small delta T. So the change in temperature is equal to the thermal diffusivity times the delta, the change in time, right, times its second difference. Okay, so that's kind of what we covered last time. Now, how? And remember, we were using circ shift. And that's a very clever way to do it. And I think I mentioned this. That's not the way I was taught to do finite difference. I was taught to do it a different way. Okay? And this is now trying to demonstrate that approach. Okay? So the Laplacian operator, okay, is essentially taking the delta x squared. You see this right here? That's in the denominator right here, okay? I'm ignoring this alpha delta time, all right? And now I'm looking for a way to express what's happening here in this part of the equation with a matrix, okay? And imagine this matrix, so see, this is like an operator, okay? So that's an operator, the Laplacian operator, and I'm applying that operator against some type of vector or some type of matrix that, so vector would be 1D of a bunch of nodes, and I'd be looking at applying this matrix against that list of temperature points, the points, the nodes with temperature, to get essentially the same thing that I've shown with second difference, and the same thing that we've been doing with circ shift, and how Professor Singer listed out. So what would the contents of this matrix look like?
I have questions for
Yeah.
the matrix for the 1D finite difference.
Sure. Yes, that's what we're doing. So this is operating, right? So in the end, okay. If we go back to the heat equation, this 1D problem, and now we've broken it up. Let's say this is the 1D, right? So remember we had the bar, and we had all those different nodes marked off in the bar, okay? And we could say, hey, this is like x sub I, this is x sub I minus 1, this is x I plus 1, right? Or we have like an x1 on one side, we have like an xn on the other side. You know what I'm talking about? Right? I'm talking about the discretization of a bar, something like that, where we could call this like x1, x2, right? And it just literally, dot, right, all the way to the end, and this is going to be something like xn. Okay? And so you're doing these, you're keeping track, right? This is an accounting problem. You have to keep track of the temperatures at each of these locations, and we're applying this finite difference to do that. Okay, now does this look a little more familiar? So now the question is, let's say that I have like a T1, T2, T3, Tn, okay? and I'm going to erase this in a minute, but it would be, because see, this is just the operator, but this is essentially being applied against T1, T2, T3, Tn, right? So in the end, what you get out of this is another vector with all the the temperatures at the different nodes. Okay, but I'm going to delete that because this is just the operator we're describing. So yes.
The matrix.
Yeah, what would the matrix, what would it look like in there?
One diagonal, two diagonals, tridiagonal matrix.
Okay, all right. Maybe something like this?
Yeah.
Okay, so you have one, right? And now you're like, oh, duh, right? This is 1, all right? This is -2, and this is 1, right? And this one is the one in front. So this one would really be this one over here, right? But it doesn't really matter because I'm adding both of them. And like this one would be like the one behind it. Okay. Can you kind of see that, how we're going in this analogy? Any questions on this? Yes. Yes. The blasted boundary conditions. Okay, so I need to do something special there. So on the left side, if I said, this is just this case, if I had a fixed temperature on that side, then I would just put zeros across the top. Okay? And then I would have to like, I'm going to put your temperature at this value. Okay? So you're absolutely right. This is the center difference, right? So it doesn't work at the edges. Okay? So then what would happen? Here's another boundary condition. At the right side, let's say, of this thing. Okay? And this one we're going to say it's Neumann. Okay? And I actually went back and I clicked on the link for Hello Newman. And I'm sorry, I think I told you it was George in his interactions with Newman. It's actually mostly Simon Jerry's interactions with Newman. Anyway, if you have a spare moment, I think the video I put in there is like 4 minutes and 40 seconds. If you want to break. And it's probably not that funny, out of context. Anyway, but the right side here, if you have, and you're like, what's going on? 1 minus 1, this is weird. Okay, this would be for an insulating situation, okay? It's a Neumann boundary condition where the heat flux at that point on the right, let's say, or it could be on the left, but this, we're going to say this one's on the right side. The heat flux there is 0. Okay. And so this Qx, that applied heat goes to 0, and you still have to keep this other difference expression. And this would be, say, the backward difference. Okay, because it's xi minus Tx sub I minus 1. So that's how we handle the boundaries. Any questions on this? I don't think you probably should, I don't want to say this is not important. It's important, all right? So because we're covering the theory here. Nonetheless, most of us are not going to think about all this on a daily basis because you're going to be clicking or coding such that you're like, oh, I just specify the boundary condition and I say I want temperature there or I want a heat flux there. And then, the magic happens inside the computer. Now, let's take a look at the heat equation again and think about what's happening in steady state. So what does steady state mean? What does steady state mean? This is a general form of the heat equation that you can find on the internet. Okay? And it's a little bit different because they're using a U, and U is really our temperature. Okay? But the X, Y, Z, those are pretty universal. The Q is really like our Q dot. K is thermal conductivity. But I mean, what do you all see here? What would it mean for this equation to reach steady state? Yes.
The temperature is kind of constant, not changing from starting out.
Okay, so the temperature's not changing, It's not changing with respect to what? Yeah, so,
Outside versus inside.
okay, yeah, all right, that's truth. All right, and is it, and when you say it's not changing when we change what? What would be the parameters we'd be interested in looking at?
So if you change the size.
Okay.
Something like that.
Okay, yeah. Anyone else have some ideas? We're getting there. Yes. Right. So it's not changing as a function of where you are, or I mean, it could. Sorry. Yeah, it's just time. All right. We're overcomplicating it, right? So you end up with some distribution of temperature in space. Okay. Where as time keeps marching forward, it's not changing. So this is like we have a day that stays constant temperature, or we have multiple days that are constant temperature, and we end up having this room essentially get to that temperature. Okay? Or you have a difference in temperature at two locations, and then all the elements in between are going to somehow form a gradient. Okay, that doesn't change between those two locations. Right? These are some examples of getting to steady state. So the time in this case is going to go to 0, or the dt, this derivative, right? And you can see that would be on that's over here. Over here, right? This is where time is. Time is nowhere else. So when we reach this steady state, we can write it, we can simplify our expression, and it can be like this. Are these types of calculations useful? Yeah, they're useful. Can you think of some situations? I mean, I guess I described some. But any other ideas? Like where this type of thing might be useful? Sure.
Fluid mechanics.
Okay, yeah. So fluid mechanics, sure. Well, it could be a little more specific there.
If you want to describe the type of what you have and so it's not changing.
Yeah. So, let's say you're cruising, in your car at a constant velocity, or you're cruising in a jet or something, right? If possible, the velocities aren't changing. You know that there was some type of interesting transition to get there, but once you've gotten there, if you're calculating your drag coefficient, your lift coefficient, and you just stay there and you cruise for a long period of time, that's an example where you're trying to get to some type of steady state response. Okay, that's a good example. There's usually always a transient to get to steady state. Okay? Sometimes that transient's fast, sometimes it's slow, yes.
So for the steady state, it's the fact that eventually it'll just reach equilibrium?
Yeah.
Okay, so.
Yeah, so in our turkey problem, you're like, why are we talking about this in the context of turkeys? Did we reach a steady state after 4 hours? No, why not?
The temperature on the outside is not the same temperature on the outside. So, like basically, a steady state would be the temperature is uniform for the entire thing.
Right. If the temperature around the entire turkey is one temperature, right, then we want that thing to reach a steady state. Now, if I had a turkey and I had a blowtorch on one end, so I had a cube coming in, right, and I had like a constant temperature on this side, right, then I could expect that I would develop a gradient in temperature. It's going to be hotter where the blowtorch is, and whatever my air temperature is on this side, it has to be a pretty big turkey for the blowtorch not to affect that. Anyway, but you get, well, actually, it's not that bad of an assumption. It's not that bad of an assumption. So, that's when you would have like a thermal gradient in the temperature. But yes, in our case, we're running the transient problem. We're running the transient problem, and we're calling it stops at a certain point in time. But we know that the turkey will continue to heat up. It'll take a long time. Okay, so this is what, in math speak, we would do to solve for the steady state problem. What have we done there? What's the difference? Yeah?
You inverted the velocity, which would be the matrix.
Right. So that matrix we had, right, in the previous slide that we said, hey, it's 1, -2, 1, 1, -2, 1, right? And then you have some special things for the boundaries, right? You had to invert it to be able to solve for the temperatures. And so what you're seeing here is this general idea, okay, down here, that you have to do this -1, you have to invert the operator. That's kind of how finite element, that's how a lot of these techniques work. We're trying to solve, we had to invert the K matrix, is what it's called. Yes, there's a K here. Yeah, that's the thermal conductivity, right? But in general, you'll see there's a K matrix, and I want to be able to invert that to be able to find the solution. Okay. So, let's look at an analytical problem, or let's look at a problem that has an analytical solution. Remember how we did this with the ball dropping? Remember that? We said, hey, here's a mass dropping. This is the analytical solution. What did we look at? What were we trying to? Remember what were we trying to evaluate there? We were looking at the analytical solution for gravity acting on a ball or some mass. What were we trying to do? Anyone? Any recollections? What was the purpose of that exercise? Someone's in the back. What were we doing back then when we were looking at why were we looking at an analytical solution? Well, what was the analytical solution for displacement as a function of time of a ball dropping? What is the analytical solution there? Any ideas? If I have acceleration g, and I want to know displacement starting at rest. Any recollections back there? Anywhere? Andrew, yeah? Yeah, it was the 1/2 GT squared, right? So that would be the analytical solution. So we're going to do an analogous exercise, not looking at how much distance a particle travels, but looking at how temperature propagates for a simple problem. So we'll start with a bar that has a length of 1 meter. And we will break it up, okay, to have 3 spaces. 3 delta x are going to go across that 1 meter. And we're going to have our heat equation. We will do some things with the heat flux. We're going to say that we can apply heat flux of 1 watt per meter squared. And we're going to say that conductivity is 1 watt per meter Kelvin. And we will essentially try to solve this problem. Okay. And then we'll look at the left and the right boundary conditions. So the left and right boundary conditions will be as follows. On the left, we'll use Dirichlet. So the heat flux, that might be a little bit confusing, but essentially we're saying, hey, there's some type of heat flux that's being generated, okay, at these locations. Maybe you have little mini torches or something distributed along the thing, okay. But then, and so they're gonna be constantly applying that heat flux. But we have the Dirichlet and the Neumann boundary conditions as follows. The temperature at the left side, if we're going from left to right, is going to be 0, and the heat flux on the right side is going to be 0. The change, the T dot, the temperature dot. Okay. So, what does it look like? Well, what's the analytical, what's the closed form solution to this problem? What do you do? Let's see, any volunteers from over here? We'll just kind of do a general group. How would you solve this problem? We've given you boundary conditions, we've given you a differential equation. What do you do? If you were in your calculus class and they said, I don't know, dy dx equals 1 over x. Maybe that's a bad example, because that's a natural law. But like, dy dx is equal to x squared. Okay. What are you going to do? You have boundary conditions and you have this expression, yes?
You integrate from one boundary to the other.
Right, okay, exactly. So how do we do it here? Yeah, sure.
We integrate from 0 to L
For what?
for heat flux.
For heat flux, right? And what is the differential equation look like right now? What is it that we would be integrating? Or what would be the expression that requires integration? This is a 1D problem. It has a scary gradient or a scary Laplacian operator in front of it, right? In 1D, what does that Laplacian operator turn into, though? Anyone still kind of over in this general area? The Laplacian? Yes, you're okay. Yes, just tell me. You got it. Just say it. Well, in this case, it's a gradient of the temperature, or it's a Laplacian of the temperature. I keep saying it wrong. Huh? Yeah, and not just dt dx. It's the second derivative of temperature with respect to x. Okay? Is everyone seeing this? This is kind of important to get the idea across here. This, yes, it was a PDE, meaning a partial differential equation. But we're doing the 1D case, and we can just then make it a regular differential equation, and we've made it simple in that it's a steady state problem, so that we have no time dependence. We only have dependence on space. Okay? Everyone see what we've done here? Okay? So this is the differential equation that we have to integrate. So how do we integrate this? You in the gray. What do you think? Right? Yeah, with the yellow thing in the thing. What do you think? How do we integrate this? Okay, okay, next to you? Yes. This shouldn't be that scary. Yes, in the back, yes. Right, so, okay, okay. You know what? Yes. So let's now, how do you integrate this? Okay, this is making it better. Yeah, okay, what do you say? What do you do?
You move the dx squared over, you take the first integral of the negative x dx equals dt, and you do it again, it's negative 1/2 x squared.
Yeah, okay? Yeah, so let's do it this way. Does that sound okay? All right, so we say, we're doing indefinite integrals, and we just do the first integration of the second derivative of t with respect to x. Okay? And then we get this dt dx. We have to have a constant there. We'll call it a. We could have called it c. And then we do it again. How do you solve for the A and the B? Over to this side of the room. But not this part of the room, that part of the room. How do you solve for A and B here? Yes? Yeah, right? So which boundary condition do you use for solving for A? Yeah, that would be probably a nice choice, right? And then for solving for B, you would use, right, you would use the Dirichlet, right? So for B, you would use Dirichlet, and then you could use the Neumann for boundary condition for solving for A. So, we can figure out here that B is equal to 0, and we can also figure out that A is going to be equal to positive. Okay, so the result is that expression. That is the analytical expression. So if you had this hypothetical problem, you would not need to do the finite element analysis. Yes, did I make a mistake?
No.
Okay, good.
One little question.
Yes.
Would it be better to do full antiderivative and plug in the constants? Or would it just you can just plug in the constants once you get the first antiderivative?
Yeah, sure. Yeah, you can.
Does it not
Yes.
matter?
Yes, you could have said, hey, I've done I've taken my first integral, and I've got a dt dx, and now I'm just going to figure out what A is. Yes. Yeah. Either way, it's good.
It doesn't matter.
It does not matter. Okay. If you like more variables, then you do it this way. If you want to get rid of those variables quickly, then yeah, go ahead and step by step. Good. All right. This is the analytical approach, which means that if we're thinking about errors, remember we thought about errors with the Euler method versus the analytical 1/2 gt squared over 1/2 gt squared, right? We're going to do the same thing. We can use this approach to look at the errors that might be involved with the finite difference method and also with the finite element method. Okay? This would be essentially trying to demonstrate convergence by method, whatever, 1 or 2. Ground truth. This is a case where we have ground truth. And ground truth is valuable in many cases. Baby steps. Baby steps. So this would be like, oh, I have a new code. I'm going to try something that I know the answer to. And you'll see that. COMSOL, different packages, they have like test codes like this. If your code is implemented correctly, this is the result you should get. Check. Okay. So, how can we do this with finite difference? Well, we can break it into different nodes, different spaces. There are 4 nodes, there are 3 spaces, and we can talk about what's happening at each one of these nodes. So at node 1, okay, boundary condition. It was told, Dirichlet, it's got to be 0. Okay, so we better stick to that. Node 2, we can use the center difference approach for the second derivative, right? Because now we know that this is a Laplacian operator, which gives us the second derivative. For node 3, we can do the same thing, all right? But now we're looking at what's happening between, we're using nodes 2, 3, and 4 to solve this. And at the right, this is a little bit trickier, all right? But we can use this is now using the backward difference, okay? And we have to also think about a Neumann boundary condition. Okay? And so there is what the matrix looks like, and this is what we would want to solve for. Okay? If you want to go back, so this is node 4, right? This is Neumann, where it's 0. I don't know if I want to go back. Maybe I will go back. Okay, and you have to believe me a little bit here, all right? But if we go back here, this is what we were talking about. The right boundary condition is insulating, Neumann, it's equal to, the Q dot's equal to 0. So then you just end up with this single, all right, difference here, the backward one, all right? I saw some looks, yes.
The other x, delta x squared.
Yes, yes, yes. But then this ends up, yes, that's truth. But because we have the q dot equal to 0 there, it ends up only having the single terms as we have there. Okay. So this is what the matrix looks like. Okay. This is essentially our Laplacian plus boundary conditions matrix. So when we form this problem, okay, we need to solve for what? We need to solve for T1, T2, T3, T4. So how do we go about doing this? Well, you say we have to take the inverse of that matrix. Do we? So what happens when we do that? You've got 0, 0, 0, 0 in that first row. 0 times T1 plus 0 times T2 plus 0 times T3 plus 0 times T4 has to somehow magically equal a constant. So if you put this in MATLAB, what happens? It says no, I cannot do that. It gives you the int. It's like, forget about it, right? So what we have to do is we actually take just the innards, this part here, and this is invertible. Okay. And so then we have this problem that we've formulated, okay? And we can use MATLAB or whatever we want to do. We can take the inverse matrix and then we can solve for T2, T3, T4. Okay. What is T1? Right, this is a classic math question. Get 0 or 1 and you're probably right half the time. Okay? 0, right? Because we said that boundary condition on that first node on the left, it was going to be, it was a Dirichlet boundary condition, and so it had to be 0. Now, and so this is the same. So this is a finite difference approach, and this is a steady state response. And is it the same as our analytical solution? Excuse me. No. All right. And what's the classic answer? If you want to improve the accuracy here, what do you have to do? Sure, yes.
More nodes.
You need more nodes, right? You need more nodes. That's what you have to do, right? So if we were to increase the number of nodes there, right, we'd have like T1 through like, I don't know, T100, we would begin to see that this solution ends up being closer to what the analytical solution is. Now, let's start talking about the finite element method. And this is where you can go to sleep. All right. So, introducing strong and weak statements. As you can imagine, in an argument, if you have it being strong, it means that what you're saying is valid. Okay. Record or mind blowing, right? Weak statements. They're kind of good. It's okay. You know, we've had a lot of political debates over the last bit in our country. maybe for a fair share of weak statements. Okay? And some strong statements. But we're going to use both of these strong and these weak statements together in different ways to be able to get another approximation, to be able to do some solving. All right? So here is strong statement number 1. We believe in the heat equation. Okay, that's nice. Another strong statement. Okay. For 1D, okay, we can write it but in the same form, but multiply both sides by some function. If you multiply both sides by the same function, we'll call it v of x here, then this should still be true. So these are strong statements. Another strong statement is that if I integrate both sides, or I can equate the integral of both sides of this equation to each other. I can use integration by parts. Okay, so this is also we're going strong. We've done nothing that is what we would consider questionable. Okay, we've done nothing weak. And then if we use integration by parts, we can write the du is equal to this, dv of x, and the v is equal to the kdt dx. And we can rewrite the expression like this. I don't expect you to have, this is a nice class in that you don't have to have exams, right? So you're not going to have to do this. And even you could argue that the finite, what's going on in the code, it's based on this derivation, but it's not like, how do you say it? It's not doing all of this, right? It's done it once, we know what it is, and then it does a couple of other things which we'll talk about. Okay. So these are now up to this point, strong. Everything's good. Here comes our weak. Our weak statement is, you know what? I want, and it's not obvious to me at this point, or wouldn't be obvious to me at this point, to say y, but we're going to say, we can make this term 0 by having the v of x equals 0, or the derivative of the temperature with respect to x being 0 at L and 0. Okay? So, you could see that, all right, if 0 times anything is 0, and if one of these two expressions is equal to 0 at both L and 0, then we can say this part of the expression is 0. And why do we want to do that? Because we prefer not to have to solve that. Okay? This is an engineering approach. So this is just copied over. All right, same exact thing we have. Okay? And so this becomes what's called a weak form of the heat equation, where we say, forget about that part that was complicated. I don't care about it. All right? We could kind of say, it's nice, okay, but I'm gonna use my UDV stuff that I've got here, right? I've got my nice U, I have my nice DV. I can kind of put those things in right here, okay. So then, or it can be written this way, okay. The Galerkin method. So what Galerkin said. Now, do you ever you've done some differential equations, right? Where you're like, I need to take some guesses at what the solution looks like, and I'm gonna have like a sine of x plus b sine of x plus c sine of, like I'm gonna have a whole bunch of, like I'm gonna have a series, kind of like Fourier series, right? And then I just gotta guess the coefficients to fit to give you my answer. So the Galerkin method says, the temperature profile in our 1D or our multiple dimensional problem, it's going to look something like this. It's going to have some constants, some coefficients, we'll call them t's, and we're going to have some trial functions. Okay, they're going to be whatever they are. They're functions of x, of location, and we can say that the overall temperature distribution is a function of this stuff. And so we're going to use what's called the symmetry or the symmetric formulation and say that the v that we put in there, that we multiplied everything by, we're going to say it's equal to these u trial functions. Okay? And these v's and these i's, these are called test functions or basis functions. Okay? And so all these trial or basis or test functions, those are going to be what we need to solve. Okay. So now we're getting into what does the computer have to figure out? Essentially it has to figure out how to solve these equations. So the new weak form of the heat equation, okay, can be thought of as these linear combinations of these test basis trial functions that we've inserted into this weak form of the heat equation. Okay. So now you have a bunch of summations of all these parameters. And you go further, and if you think of something times something, all right, this is a little bit of a stretch, okay, you can begin to think of you're projecting something like a dot product onto something else. And so what ends up happening, all right, is that you have these tests and these basis functions, and you're multiplying them against each other, and you're going to have them overlapping. Where they overlap, you're going to have a non-zero expression. Yes? Go ahead.
Your inner product?
Yeah. Well, so it's more like taking, yeah, I mean, or you could almost think of it as like, if you've done some signal processing, you can almost think of it as like a convolution.
Oh.
Okay? All right? But yes, you're essentially looking at these values, and if they overlap, you have something. If the distributions are separate, then they're going to be zero. Okay? Okay? So here, over that overlap, right? And we kind of did this in DMC a little bit, right? Remember, or you've done this in some of your statistics classes, right? When you're looking at reliability, right? You were like, oh yeah, what's the distribution for failure? What's the distribution for the loads? And if the distribution of the loads was way far apart from the distribution of the failure, then you know that you have essentially zero probability of failure, right? But if they overlap, boom, that's definitely non-zero chance of probability. Okay, so this is the basic idea, and now we'll introduce some rules for these trial functions. They should equal 1 at a specified node and 0 at all other nodes. Okay, that's an interesting rule. Okay, so that's like saying that t, if I have a function, it's maybe at t3, t sub 3 is 1, but at t1, t2, t4, t5, t6 is 0. Okay? And they can have overlap, okay, between the nodes. And they should satisfy the boundary conditions in the weak form. All right? So, like, there are books on the finite element method, so this is just like the not Craigslist. What's it called? the Cliff Notes version of it, okay? I guess now people say check. Whatever, but it's like, this is the abbreviated version, okay, of what's going on theoretically. So, we can say this is a valid function, where at one location, when when you have u sub I at x sub I, that's equal to 1, but if u sub I of x sub j, if the I and the j are not the same, then it's equal to 0. So these are temperatures at every node, and they have an interesting looking shape. Okay. So we'll call this shape, okay, and again we're getting a K matrix that we invert. The shape that we usually choose, or we might choose, okay, is the hat. Okay? So you see the hat satisfies this condition. The hat is 1, or satisfies these rules. It's 1 at a specified node, and then it goes to 0 at its neighboring nodes, and then it's 0 at the rest of the nodes. Okay? Does that look like a hat? I don't know if it looks like a hat. Is that your idea of a hat? Triangle? It could be a triangle, if you want to call it a triangle, right? So there are multiple ways. Tent, those are the other forms of these functions, the other creative names of these functions. And so when we start multiplying against each other, if we can get these kind of different values, ups and downs, all right, in some different regions, okay, such that we can then go about creating a stepwise distribution for whatever we're interested in. In this case, we're interested in temperature. And that makes sense, right? We're saying that the element itself has a constant temperature across it, maybe. Or we're saying that these functions are doing this. Okay. And in fact, that's actually not exactly true, because usually we think of the temperature of the nodes, and so that temperature distribution is going to be changing. So you can have these flats with the products, you have the flats with the products, but the temperature distribution will be changing across the nodes. Otherwise, the temperature would just kind of have to be flat across the whole thing. Okay? So again, speeding through all this, if we use the finite element method and these hat functions, as we see here, we can assemble the K matrix, and we can solve for this distribution. Do all this out, and what does it look like? Boom. What are you looking at? This is this is the temperature matrix right here. Okay, this was solving. We had to use this, invert, and then we solve for these temperatures, and this is what we get. And if we go back to our analytical solution, it turns out it's dead on. These sets of points, they match the analytical solution exactly. What's the difference, though, between the analytical solution and this finite element solution? Finite element is only telling us values at given locations, whereas the analytical solution, it can tell us what it looks like in between locations. Right? So we have to use more elements now to get a better, closer to a curve, a closer fit to a curved surface. All right. There are multiple ways to improve the accuracy. You can change your basis functions. You can have different types of shapes, elements, nodes, intermediate nodes. So like if you're doing 2D type stuff, you might have a rectangular element, but then you see that you put these extra nodes on these walls and then another node in the middle. Okay, and then you can have different forms, different test functions, different basis functions across different polynomials to describe what's happening across these elements. And it can look something like this. All right, and you can look at these, I know in your spare time, you're going to be looking at this kind of stuff for fun, right? Transit simulations, it gets nastier, all right, but just take my word for it. ANSYS does a good job. All right, and then these are simulations we did in our lab in COMSOL many moons ago, all right, to try to simulate the behavior of these different actuators. And these are the physical systems that we made. So well, I'll have to be honest. Often what happens is we go ahead and we, as an experimentalist, it's kind of sad, but we get the experiment to work, and then to convince people that we know what's going on, we go back and we get the simulation to work. And then we show, hey, we were able to simulate this behavior, and it matches our experiments. All right? That's the life of a mechanical engineer. So these we got working, all right? But we needed to do this to show that we could like understand what's happening. Okay. And actually, there's some issues with the accuracy of this. So anyway, today, what have we done? Hopefully not. Hopefully you're still awake. But we've transitioned from finite difference to finite element method. We introduced what it means to take the weak form of an equation, the heat equation. We introduced this idea that you can have these functions that fit the profiles, and then you have to solve for these coefficients of these functions, and that involves inverting a K matrix, and then finite element can be very accurate, but it can be a little bit costly. Any questions? Yes?
So the weak form, you got more accurate solution in the weak form
Then finite difference, yes.
than just
Right. We did, but it was a lot more complicated, a lot more math than using the finite difference. So if you're interested in brute force, and you don't care, finite difference can be quite nice because it's simple.